Good evening. How is everybody doing tonight? Hope all is well. We got a lot to cover today, mostly a lot of theorems. Got a couple example problems, but we're going to throw a ton of theorems at you today. Again, we're back on circles and the lines that intersect them. Today we will be talking about chords. And chords are going to be defined here very shortly. All right, we already know what arcs are. We did that a couple of weeks ago. Central angles as well. We already know that. But they're all related. Also, perpendicular bisectors are going to come into play. But basically what we're talking about, we're going to be looking at what are chords. So we got a ton of theorems. What's the best way to remember all of them? Or more specifically, how to use them, because these theorems are going to help you solve problems. Our only vocab today is chord, and we will be looking at Pearson section 12.2. I will only do two examples at the end. Again, you will want to check on your own examples and follow through, make sure that you are understanding as you go along. So cross-reference with the book if you must. Okay, so a chord, basically, is a segment whose endpoints are on the circle. Nice and easy. PQ is a chord, all right? Now, I also want to point out to you, remember, we've also got an arc here that's called PQ, and they are going to be totally related. These are related arcs, okay? Arc PQ and chord PQ are going to be not interchangeable, but intertwined entirely, okay? So keep in mind that we've got a chord right there and a related arc that goes with it. Okay, so going back a couple units, I hope you remember that we could define an arc in terms of its central angle. So arc PQ, remember, was defined in terms of the angle that intercepted it, okay, the angle that's formed here and here, all right? Arc PQ was defined, in other words, we could also call this angle x, right, or x degrees as a way of measuring arc PQ. Okay, so remember how we did that. Now, know that for this circle, or for any congruent circle that's just like it, anytime we have a central angle that's x degrees, all right, well, this arc here also has to be a measure of x degrees, therefore must be congruent to PQ. Okay, now by extension, the chord here also has to be congruent to any chord that I would form with any angle, any central angle of a measure of x. Okay, let me try and break that down for you a little bit easier, make it a little simpler by breaking it down. It's not that complicated. We're seeing that for any circle or any pair of congruent circles, if those central angles are the same, we're going to intercept congruent arcs and have congruent chords. All right. Basically, we got three theorems and converses that are going to help this make sense. All right. Or break it down for you again. All right. First one is really just telling us if angle x equals angle y, then arc PQ must be, let me put a mark there, arc PQ must be congruent to arc RS. Simple enough? Okay, if x equals y, then the two arcs must be congruent. The converse is also going to hold true. Okay, if, let me go back here again. If RS, arc RS is congruent to arc PQ, then angle x must be congruent to angle y. Simple enough? All right. Next one, Theorem 12.5 is related. It tells us that if x is congruent to y, then segment PQ, chord PQ, is congruent to chord RS. Okay, its converse also holds true. If RS is congruent to PQ, then the angles must be congruent. And finally, Theorem 12.6, not finally, but to move on, Theorem 12.6 tells us if arc PQ is congruent to arc RS, then segment RS is congruent to segment PQ. Okay, converse as well. We also have that if, go back here again, if segment PQ is congruent to segment RS, arc RS is congruent to arc PQ. All right, pretty much everything is related there within the same circle, or if I were to have another circle that was congruent to circle O, angles, chords, arcs all have to be the same if they all are related the same way. Good, good. All right. Next thing we got to do is go back again a few, well, even a little farther, and remember, if we're measuring a distance from a point to a line, we would always take the perpendicular length, the length of the segment that is perpendicular between the point and the line to define that distance. Okay? Just a way of going to this next theorem, which tells us that if two chords are equally distant from a center of a circle, then they must be congruent. In other words, theorem 12.2 says that if we've got the same distance from the center to a pair of chords within a circle or within congruent circles, then those two chords must be congruent. If OT is congruent to OU, then PQ must be congruent to PS, to RS. Okay? Its converse is also true. If our PQ is congruent to RS, then they must be equally distant, or OT is congruent to OU. Theorem 12.8 is telling us that if we have a diameter, ST, and it is perpendicular to a chord, like PQ, then we know that arc PT must be congruent to arc QT, and we also know that segment UP is congruent to segment UQ if we have a diameter perpendicular to the chord. Next one, as long as PQ is not a diameter, if this chord is bisected, or if diameter ST bisects this chord PQ, then ST and PQ must be perpendicular. Finally, theorem 12.10 says if ST is the perpendicular bisector, so we know this is true, of PQ, then point O must lie on ST, or in other words, ST must be a diagonal. And I know that's a lot to throw at you, but we basically, you'll see how they work out when you get a little practice on them. So again, go back and check them out if you must. Let's do a couple quick practice problems. One that uses the last theorem. Last theorem's about the diagonals here. Okay, will look like this. All right, what's the radius of circle O? Here's what we need to check out. We need to check out the fact that we've got a segment OP here, right? Segment OP, okay? And it is perpendicular to this chord right here, right? It also goes through the center, which means that it is part of a diagonal, okay? And we had the theorem back there a while back. That's a really ugly line. Let me go back there. So it's part of a diagonal. And we had a theorem that told us that if a diagonal is perpendicular, so where was it? If a diagonal is perpendicular to the chord, okay, then the parts of the chord are congruent. So we've got a diagonal, and it's perpendicular, and basically what it's telling us is that this must be congruent to this. So if the total is 24, each of these must be 12, right? Which means we have a nice little triangle we can solve using the Pythagorean theorem. Okay, and we can find the hypotenuse or the radius, which is going to look like basically 10 squared plus 12 squared. That's not working well for me. Let me clear that off. All right, 10 squared, or 12 squared, plus 10 squared equals r squared. All right, so we solve our math there, and we find out 12 squared is 144, plus 100, or 10 squared is 244. We take the square root of that, and we find out that r must be about 15.6. Make sense? Nice little triangle we formed by knowing that the perpendicular, that a diagonal that's perpendicular cuts this thing in half. Okay, last example I'm going to do for you. Find the value of y. Okay, once again, we know that we've got something that's bisecting this. We see the 12 and the 12, and we've got a line that's bisecting it. Our theorem, one of those theorem back there told us that that means that this must be perpendicular, must be a diagonal, etc., etc., etc. Okay, 15 degrees is or 15 centimeters is a radius. We can also know that this radius right here is the same 15 centimeters, correct? Once again, we have a nice little triangle, okay, where the hypotenuse is 15. One leg is 12, one leg is y. We can solve that, and we're going to find out that y equals 9. Once again, we could also recognize that that is a 3, 4, 5 triangle, but basically this is how we did this one, by recognizing that we must form a right angle here, and we've got a side of 12 and a side of 15. And we can solve that using Pythagoras for y. Okay, hope that does it for you, and we will see you all tomorrow.